Today, we're going to talk about a hidden code, a kind of secret language that's written into the world all around us. A single mathematical formula that can describe the shape of a starfish just as easily as it can design a piece of high-tech art. It's the secret language of form, and we're about to crack it.
Okay, let's just jump right in. Have a look at these two things. On the left, we've got a starfish, a product of millions of years of evolution, and on the right, that's a piece of digital art, a future fossil created by an algorithm. One is pure biology, the other is pure code.
So what do they have in common? Well, at first glance, you'd say absolutely nothing, right? I mean, they come from totally different worlds. But what if I told you they share a secret mathematical ancestor? That in a weird way, they're actually cousins?
Yeah, the answer isn't in a biology textbook or an art gallery. It comes from the world of pure math. It turns out there's this hidden connection, a kind of universal blueprint that underlies both of these forms.
And here's the secret. They can both be generated by the exact same mathematical formula. Think about that. One single equation is the source code for the starfish, the sculpture, and just countless other shapes we see every single day. So what is this incredible thing? Well, it's called the Superformula. Let's dig into what it is, where it came from, and how it actually works.
The journey actually starts way back in 1818. A French mathematician named Gabriel Lemay was trying to describe the shape of crystals. But then the idea kind of sat on a shelf for almost 200 years, until 1997, when a Belgian scientist, Johann Gillies, dusted it off and gave it this radical new power.
So it all starts with these shapes, which Lemay called superellipses. You can just think of them as this whole family of shapes that includes perfect circles, perfect squares, and all those in-between squircle shapes with the rounded corners.
Now, Gillis's big aha moment was realizing the superellipse was kind of stuck with four-way symmetry, so he added new parameters to the equation. Think of them like new dials you could turn. And the most important one, a little something called m, controls the rotational symmetry. And here, you can really see that m parameter go to work. I mean, just by tweaking that one number, the formula just spits out all these different shapes. Things with 3 points, 4 points, 5 points. It creates flowers, stars, and polygons, all from the same basic recipe. It's incredible.
But making cool 2D shapes is really just the beginning. The real power, the magic of the Superformula, is unleashed when we take it off the flat page and start building a whole universe in 3 dimensions.
So how do you get to 3D? Well, it's not just about stretching a 2D shape. It's way more clever. The breakthrough was figuring out how to take two separate 2D super shapes and, well, mathematically multiply them together.
The easiest way to wrap your head around this is to think of one super shape as the object itself and the second super shape as the path it moves along. So if you take a circle and move it along the path of another circle, you get a perfect sphere. A circle moving along a straight line, that gives you a cylinder.
And this is the results. It's absolutely stunning. By combining different super shapes for the object and the path, you can create a practically infinite universe of forms. Everything from simple prisms to these unbelievably complex organic-looking structures.
And here's the part that just blows my mind. All of the information needed to describe one of these super complex shapes can be stored in less than 40 bytes of data. That is smaller than a shortcut icon on your computer's desktop. Amazing!
Okay, so this is obviously more than just a fun math toy for making pretty pictures. It's a seriously powerful tool with some profound real-world applications, both for understanding the natural world and for building better technology. In biology, it turns out that nature has been using this code all along. Scientists have found the Superformula is an astonishingly accurate model for thousands of natural shapes, the cross-sections of plant stems, the shape of a cactus, the tips of roots, and yep, even our friend the starfish.
Now, let's look at a perfect example from engineering, the humble yogurt pot. A normal circular pot is actually really inefficient. When you pack them into a square box, all that empty space between the circles is just waste. The challenge was to find a better shape.
So, using the Superformula, engineers design what they call a supercircular pot. On the left, you see the original. On the right, that's the optimized one. It looks almost square, but it's not. Its corners are curved with mathematical precision, so the pots can nestle together perfectly.
Now, that tiny change in shape led to an almost 3% reduction in the plastic needed. And, 3% might not sound like a lot, but when you are making millions of these things every single day, that is a massive, massive saving, both for the environment and the company's bottom line. And it's not just about saving material, it's about making things stronger. A classic engineering problem is that stress concentrates around a circular hole in a metal plate. But by changing that hole from a perfect circle to a specific superellipse, engineers can slash that peak stress by over 13%, making the whole part stronger without adding an ounce of material.
So, this elegant little formula is really just beginning to change how we design and understand our world, from stuff we use every day to really high-tech gear.
And the applications are getting more and more advanced. Right now, researchers are using the Superformula to design next-gen antennas with really unique properties. They're even shaping the mirrors inside high-power lasers to create more efficient, precisely shaped beams for manufacturing.
You know, it really feels like we've just stumbled upon one of the universe's fundamental building blocks. As its creator, Johann Gili, said himself, the formula unveils a very basic geometry of nature.
It kind of makes you look at the world a little differently, doesn't it? I mean, it leaves you wondering, if one single elegant equation can describe a starfish and a yogurt pot, what other simple rules might be hiding in plain sight, just waiting to be discovered, quietly governing all the beautiful complexity around us?